So we have seen this. Okay. So endurance and range for jet. So engine is identified by thrust. So of course we have two schemes. For a jet engine, normally the engine is described using thrust. But for a propeller engine, the engine is described by power. So therefore, first of all, we will assume that we have jet, or thrust is the method that we describe the engine. Here, I'm not saying that thrust is constant. This is assumption. I will assume it, but not now, later. Okay. First of all, endurance. Recall for straight and level flight, under our usual assumption, always we have thrust equal to drag and lift equal to weight. Then we can determine the rate of fuel consumption like this. So fuel consumption, CT here, or this specific fuel consumption, CT because of thrust, okay? And here is amount of fuel flow. So this is WF, so this is F for fuel, and dWF over dt, this is the fuel rate, or fuel flow. But of course, W, it means weight. I need to use weight instead of mass, okay? So equal to CT into T thrust. So of course I can replace thrust by drag. Then I have CT equal dWF over dt equal CT into D. Okay. So from this equation here, or this term here and this term, I can isolate dt here from here. dt equal to dWF over CT into T. So this is the time. In order to, I need to calculate the time. Of course, I need to integrate. So endurance, we can also note that the rate of fuel burn, this one, okay, is the same as the rate of aircraft loss of weight. Very important now. So how much we have fuel consumed, the weight of the airplane reduced by the same amount, okay? Hence, we can write dWF equal to minus dW. So the time equation can be written as this. So this equation from previous slide equal to, or become like this: dt equal to minus dW over CT into T, or equal to minus dW over CT into D. Simply, we just replace, instead of having fuel decrement, we made the total mass of airplane decrement. Okay. So now we can integrate equation 9. This is equation number 9. We can integrate equation number 9 over the time of a flight. On the left, this one, and over the change in the weight on the right. So here we have time of a flight, and here we have change of the weight. So therefore the endurance E, we give it E for endurance, equal to T2 minus T1 equal to minus, this is the minus over here, integration minus W1 to W2 dW over CT dt. Now, in order to perform, obviously, in order to perform this equation, we need to know what is the relation between CT and W, and what is the relation between D and W. Of course, it's difficult to say what is the relation, but I can assume some assumption and assume some flight schedule. Then I can know this relation and I can integrate it easily. Let us start. Also, similarly, before going to integrate the endurance, I will first make the range. We can compute the fuel burn per unit range as follows. So airspeed is given by, of course, airspeed V equal to ds over dt. S is the distance. So where S is the range variable. Okay. Then we can compute the fuel burned per unit range as follows. So dW over ds, this is amount of fuel, and this is distance. Okay, so how much we have fuel divided by how much we have distance. This is fuel burned per unit range, equal to dW. Here I will just only include ddt. Here I include dt, and here include dt. So dWf over dt, ds over dt. This one here, I have seen this from previous slide. This is equal to ct into t. ds over dt, this is speed, v. Okay, so also instead of t, I can use d, drag. So in a similar manner, we can rearrange equation 5 to get the range equation. So the range equation between 2 points equal to integration between two weight at the start and weight at the end. And then here we have v over ct into dd over d. Okay, so of course from this point here, ds. Okay, so therefore I can summarize these two equations like this: the endurance here and the range here. So now I need to integrate. So we need to know ct to integrate range or endurance. We need to know ct into d, and we need to know for range v and ct and d. So we need to also, these functions are not unique and depends on the flight schedule. Typically, flight schedule are, we have here just an example. Maybe you have many flight schedule, but maybe the pilot, he decide to fly at maximum endurance. Another pilot, he want to fly at maximum range, or to fly at constant airspeed, or constant angle of attack, or constant altitude and constant airspeed, or sometimes constant altitude and constant angle of attack, or combination of these two values. Okay, so every type of flight produce different range and different endurance. So first of all, need to determine the flight schedule, then you can calculate the range or the endurance. So let us first start with the endurance. I will assume this assumption. First of all, I will assume the thrust is constant, ct is constant, and also flight path is nearly level, left equal to weight. I will also select constant angle of attack. Of course, constant angle of attack, it means CL equal to constant. Since CD function to CL, then CD is constant, CL over CD is constant, then I will back to this equation. I can easily integrate. Of course, I need to replace here W over D here. I can replace it by CL over CD, which is constant. Then I can make the integration very easy. So endurance equal to half 1 over CT L over D logarithm W1 over W2. So this is the weight at the beginning, and this is the weight at the end. So this is simple equation to calculate the endurance within these conditions. Be careful, this is correct within this flight condition or this flight schedule. Okay, so this is the same equation, but we need to discuss it. For long endurance, of course, this is good characteristic to have very long endurance. The equations here says that if you need to maximize endurance, what you have to do? Obviously, you need to to have L over D. So let us discuss term by term. The first term here, we need to have CT as small as possible. Of course, this is the fuel consumption of the engine. When you have very good design engine, the engine consumes very little fuel. Let us discuss this term. What does it mean? This is L over D. L over D, this is aerodynamic efficiency. So L over D should be as large as possible. Also, this is express the aerodynamic efficiency or the quality, the design quality of the aerodynamic. Therefore, if you need to design aircraft to maximize the endurance, actually you need to focus on this term. You need to maximize the aerodynamic efficiency. Okay, so the third term here, the weight ratio, weight at the beginning to the weight at the end. This term should be as large as possible. So W2 equal to W1 minus W fuel. Okay, so of course to minimize W2 you need to have very large amount of fuel, and of course so there in this case W2 becomes small and this ratio becomes big. Okay, so let us now also we have another flight condition. Let us select constant altitude and constant airspeed. In the previous slide, I will just remind you, constant angle of attack only. But here, constant altitude, constant airspeed. So, of course, here I will use, of course, my eyes here. I need to integrate. So I need to work out D. Okay, D, I will use this equation. So here we have velocity. So velocity is constant. Okay, and here we have also velocity constant, area constant, density. Since constant altitude, density is also constant. So the only variable is weight. Why? Because we have fuel consumption. So this equation can be simplified in this format: constant plus constant multiplied by W squared. Okay, so now, sorry, here should be right A and F are constant. So I will substitute here, then I got this. Endurance integration, W1 to W2, here we have constant and here we have constant. I think this is easy for you to integrate, and the integration is well known, and then simply you got this integration, this relation. Okay, so let us discuss or write this equation in different way. So you can write it in different way. So here we have CL1 and here we have CL2. This is CL1, the lift at the beginning, and here CL2, the lift at the end. Okay. So here is an example. You can have it, and here is the solution. I will not go through this solution. I think just direct application to the relation that we already have. And here is another slide, other page for the solution. Okay. Now we need to also calculate the range. We have 5-minute time left. I think it's enough to finish the range. The range equation, we have seen the range like this. The only difference between range and endurance, here we have velocity here. Okay, so we need also to use the same, roughly the same assumption, and also we need to select flight schedule. By the way, we will see two schedules. In the note, I will give you note. I think you can have the note from California University. It contains the same material here. So please go back to this note. It includes everything. All text is included. Here now I will start with flight schedule A. Flight schedule A, I will assume in this schedule altitude is constant, it means density is constant, and angle of attack constant, of course, it means CL and CD constant. So this range equation, velocity from lift equation like this, and 1 over D, it's mean equal to CL over CD over W. Okay, we have seen this from before. And now this all terms are constant. We have only this one is variable. So I can integrate from 1 to 2. So the integration like this, very easy. So again, we need to discuss how can we maximize range. So this is schedule A, and this is the assumption, and this is the range equation at this assumption. And here we have the conclusion. A small CT, this is CT, what is CT here? What is here CT? Sorry, because here I'm writing capital letter and small letter, but I think you are smart enough to know this is the specific fuel consumption. The lower that the specific fuel consumption, trust specific fuel consumption, the farther you can fly, of course. This is obvious. And now the equation says this again. And also, sorry, this is repeated, okay? We would like to fly at high altitude, this is to minimize rho. If you minimize rho, you maximize range. To have low density. Also, we would like to maximize this term. If you maximize it, we can maximize range. Also, we have seen this from before. We've seen that derives the condition to maximize range. We have seen the same result. Also, we would like to carry lots of fuel. If you have more fuel, then this number is small, and this one is big. Then we have big range. Okay. So let us discuss the schedule B. Here in schedule B, we have constant angle of attack, and we have constant airspeed. So in the same philosophy we have seen before, constant angle airspeed, V equal to constant, and constant angle of attack, it means CL over CD equal to constant. And then we can go back to this equation and substitute, and CL over CD here constant, V constant, CT constant, outside of the integration, and then we have this relation. Here we can integrate it easily. This is the integration. And now we have this is conclusion of this note. We can note that this expression is just the endurance equation for the same condition, constant angle of attack in the previous equation, or equation 13, multiplied by the constant airspeed. This equation actually is valid for all flight condition. However, to maximize range, we need to maximize V over CL over CD. So this is the look here. We need to maximize V CL over CD in order to maximize the range. So equivalent, actually this is equivalent to maximize CL power 2 over CD, as we have suggested previously. Okay, so schedule C, it's explained in the note. I will not go through this one. I will leave it to you. So please study this one, so you have to understand it. So constant airspeed here, V equal constant, and constant altitude rho equal to constant. So of course, parabolic, we also always assume parabolic drag polar. Okay, so here by this now, I think now finished. I will stop at this point. So if you don't have any question, I will end this session.